In this lecture, I just want to prove a very, very important theorem. In the thesis of that guy, I forgot his name, in Inria, he proved that local RIP for sketching operator. I think it is on page after 100. So he proved the theorem. First, I should say the theorem. Consider a model. You can just download the thesis and just read the theorem. But I just try to say it quickly. Consider a model theta inside B, a fixed distribution in the model p theta in theta, a kernel K with RF expansion FR and alpha, an error greater than 0, and a sketch size. So we want to have a minimal sketch size. This is the meaning of dimension reduction in machine learning. Of course, the people who like data structures, their motivation is something else. They want to save and use less resources. So they want to reduce their space. So sketch size M such that RF expansion is admissible for the model theta with constant W alpha less than infinity and error eta. The second part of the theorem says the normalized second set that I introduced in the previous lecture has finite covering numbers. So N with a norm FR and second set of P theta model theta is less than infinity. So we have a finite covering number. So this covering number is finite. And the third part says that, the third assumption, of course, is that there is a pseudometric d lambda and a constant such that p theta minus p prime is less than w alpha p theta minus p prime k. And finally, the sketch size satisfies M greater than, just like Johnson-Linderstrauss lemma and many things that you need at least some dimension to do something. We do the same thing. We say M is at least greater than CW alpha squared log n over rho for some rho greater than 0. And interestingly, C is 1760147 is a universal constant. If these four assumptions satisfies, then if they satisfy, then the sketching A mu defined by the inner product of mu and phi, which is now psi mu omega j from 1 to m, is a complex vector of dimension m, satisfies, so this one satisfies the non-uniform LRIP for model theta and elements if the model p theta with constant alpha equal to 2WL with probability at least 1 minus rho on drawing of omega j, we can say that the difference between PG and P prime G is bounded by AP theta minus A P prime theta plus this one. So let's prove this important theorem, which is the heart of this PhD thesis. So we are going to prove that with high probability, the sketching operator A for all mu in S holds that A mu is greater than 1/2, for which we have seen that we can deduce that for all P prime in theta, we can write that P theta minus P prime is less than maximum of 2A P theta minus P prime theta, which is less than 2A P theta minus P prime theta plus eta, which combined by the assumption that I said, which is P theta minus P prime theta was less than P theta minus P prime theta, yields that desired result. So in order to prove that A mu is greater than 1/2, that this holds with high probability for all mu, we prove that it holds with a finite number of mu i's with high probability, because if we prove it for just a finite number of them, then we can use the covering as usual. I mean, we can use the delta covering to extend the result to the whole domain, to the whole set. And let's P prime theta in theta. So the trick is always the same. In any proof of such theorem, we need to cover something. And if it holds for a finite number of such elements, then we can extend it to, it's like you do something for the bases in linear algebra, and then you extend it to say that everything is just a linear combination of that, so it holds as well. So we say that let's say let P prime theta is in theta be such that P theta minus P prime theta is greater than eta, then we can define mu to be the normalized difference. I mean, one of the elements in the second set, you can say. Then we draw those random frequencies from of course alpha, and the trick of this proof is that you create some interesting random variables. Don't forget that yj is a random variable because omega j is a random variable. So psi mu omega j squared. Okay, since these yj's, because they are IID, identically independent and distributed, then Eyj, you can write it as just take the expectation alpha psi p theta minus p prime theta of omega j squared, because it is normalized, but it is a scalar, so don't worry, expectation comes out. Okay, so this one is equal to 0. By admissibility, we can write psi mu of omega j squared. I'm just writing the definition of that up to here, and then I use the fact that this is less than mu fr norm of mu, and this one is less than w alpha squared, because it is, and therefore, and from this we can say that this yj is 1 minus omega 2 alpha and 1. So by lemma that I introduced in the, if you remember, I said something like this, that both L2 norm and a mu, the second norm, is bounded by fr norm. So our art is just bounding the norms and saying which one has the finest granularity. Total variation norm is here, and because by lemma I said that that's so this holds. So the variance of the yj, I should say that the variance of yj is just variance of psi mu of omega j squared is less than expectation of psi mu omega j to the fourth is equal to expectation of psi p theta minus p prime theta omega j. Of course, we have p prime for all of them, and this is less than equal to p theta minus p prime theta fr, and expectation of psi p theta minus p prime theta omega j over p theta minus p prime theta to the fourth. So this one is equal to p theta p prime theta p theta minus p theta, but the fr norm. So this is bounded by, so your variance is bounded, and using the sketch that this sketch, because you introduced the random variable yj, but now you're summing m random variables, and these things are very classical things in probability. And the theory of concentration of measure in general, there is a great book by Ludusky, I forgot his name, Ludusky, about 400 pages about concentration inequalities. So I assume that you are an expert in concentration inequality. Then, so this sum has this beautiful representation. So we can say, we can now apply Bernstein equality. Bernstein equality, what is Bernstein equality? It says that, let's go to the other page. Bernstein equality says that the probability that the sum of some random variables, but each of them is zero mean, if this one is greater than t, then it is the probability is less than e to the t expectation, sum of expectation of xi squared plus mt. And this is bounded by e to the, and the universal constant appears here, omega lambda 2. So C is that funny universal constant. So as we are almost finished the proof. So denote by n to be. So I want to find the covering. So this is the FR norm. And let mu1 till mu be a 1/4 covering of S. So we have S. We cover it by, okay, it's enough, mu1, mu2 till mu(n). We cover them by mu(n), so a union bound yields that with probability at least 1 minus n e to the minus mc w squared. We have that for any mu I, for any of these mu I can say a mu I is greater or equal to 1 minus 7/16, which is 3/4. So there exists mu I such that mu minus mu I FR norm is less than 1/4, and we have 1 minus a mu L2 norm is 1 minus a mu I. So I'm just subtracting and adding a mu I. So nothing really important. Just adding and subtracting. And finally a mu. And I said that one is less than 3 or 3/4. So because a mu I2, because this one is less than a mu I2, I proved that. So this one plus a mu I minus a mu. So we use the reverse triangular inequality. So 1 minus a mu is less than 1/4 plus a mu minus mu I. This is by lemma 3.15, this inequality. I should say it again. This is the third time that I'm writing that both mu and a mu is less than mu norm of FR, less than BFR total variation norm. So we're done. We then denote that rho is n e to the minus m c. The probability of failure is this, and we solve it for m to obtain the bound. And that's the whole proof. So now I just want to talk about real thing. So what is the application of this sketch that I proposed? I mean, the researchers of Inria proposed. It has, you can find, for example, you can estimate mixture models using the inspiration from compressive sensing. But now we have generalized it, so we have a compressive machine learning. And what you can do is that for a Gaussian p theta, you can have a characteristic function. What is your characteristic function? That's I omega transpose mu. So it has an explicit form. It's very interesting. It has an explicit form. So the characteristic function of the Gaussian mixture model is psi, phi theta, and chi. So G. So we want to minimize L from 1 to k, I